Hello, my name is Tommy, and in this presentation we are going to work our way from linear regression to generalized additive models. The intended audience for this presentation is data scientists, and it helps if you have some background in calculus and some background in linear algebra. If you don't have that background, parts of this presentation is going to be a bit hard to follow, I suspect, but feel free to give it a chance anyway. So what's a generalized additive model, or a GAM? It's essentially the orange line we see here. We're going to go away from linear regression, where we have linear functions, and have these functions that are more wiggly. It's a semi-parametric model that I believe is underused. It's very useful, especially if you want to explain a data set and understand a model. So it's a great model for transparency, and often it's quite competitive with the black box models like neural networks and boosting on tabular data. So it's a very interesting type of model, and I want to try to introduce it in a special way by building up from linear regression. Here's the agenda. We're going to talk about the need for simple models. It's going to be very non-mathematical. Then I'm going to start with the math and introduce linear regression, ridge with a link function or inverse link function. And then finally we get to generalized additive models. And we're not going to talk about the complexity and details of the generalized additive models. We're just going to introduce them and try to explain what they are in the simplest case. But let's start with the need for simple models. So if you're working in a company or an organization and you need some kind of model, the metric, the performance of the model is probably not the most important thing. I mean, sure, you want a model that performs well, that's very important, but there's all these other questions that arise when you work with models in the real world. Like, what's the purpose of the model here? Are you trying to make good predictions? Are you trying to understand your data? Are you trying to understand uncertainty? Is it important that you understand the model itself, how it works, who will it be used by, and so forth? So purpose, very important. The data is important. What's the quality of the data? How much data do you have? Do you have big data in the sense that maybe it doesn't fit in memory, so you need some specialized things to train it or to predict with it? Prediction is usually fine, but training, maybe you have several, like 100 gigabytes of data, I need some special infrastructure for that. How important is interpretability? If you're predicting, especially there's these really bad cases where people have tried to predict social outcomes, like trying to predict who should get a loan, what the insurance premium should be, who should even go to jail, things like that. And especially in those cases, you really want the model that you can understand. But even in simple engineering applications, most engineers are really uncomfortable using models that they don't understand. So it's a very important thing to consider in the real world. You can't just do like boosting or ensembles of models if the people who are going to use them have a need or a desire to understand what's going on. Is uncertainty important? Yeah, you get a prediction, but how certain is the model about that prediction? Do you want to build some uncertainty thing on top of your model, or do you want to use a model that has uncertainty built into it from the get-go? And the implementation infrastructure. How is this thing going to be run? Who's going to run it? Who's going to maintain it? How much code needs to be written? Is it going to be on-prem, in the cloud, and so forth? All of these things are really important to think about. And all of them become easier to reason about if you start out with a simple model. Maybe in the end, a boosting model is the correct choice for your application. Nothing wrong with that, or a neural network, or something more complex and black box. But I don't think there's any excuse to not start with a simple model, especially if we work in tabular data. It's the kind of simple problem that we see where maybe not a linear model, but a simple model will perform just fine. I really recommend starting with something simple, even if you know you're not going to end up with a simple thing. At the very least, you have a benchmark to compare against, and if your complex model is just marginally better on the metrics, it's probably going to be better on all of these. It's probably going to be more interpretable and easier to implement. So then I think that's a strong argument for choosing a simple model. So as I just mentioned, we have all these strengths of simple models, and I think they should be considered way more in industry and in practice. Here are some examples of simple models. And on many problems, these do perform just fine. So linear regression, classic, right? You can, once you know the coefficients, you can implement them in Excel and SQL directly. That's a big advantage in many companies and institutions where the infrastructure to run models at scale is not present. Most companies aren't Google or Facebook or these famous tech companies that you hear about. And if you want to get something up and running, starting simple and going for a simple implementation sure helps. For linear models with some domain expertise, engineering some features, looking at the data, you can often get really good results. Another simple model is a single tree, not a forest, not an ensemble, not a boosting model, just a single tree. Like imagine trying to predict the probability of heart disease or something. The single decision tree would be like, are you older than 50? Are you male or female? Do you smoke? And then just going 3 or 4 levels down, you probably have a pretty decent model already. So that's something to consider. You can print it out. You can look at follow the paths along the decision tree, prune it, make it simple, and it will probably give good results. And you can also refer to the examples that are found in the leaf. So if I'm trying to classify a patient, I can return not just the prediction for my patient, but I can return information. Maybe if it was in the real world, it would have to be anonymized somehow, but I can return information about the other patients found in that leaf. So you get like, I don't know, 10 or 15 or 50 patients in that leaf node, and you see what happened to them. And that gives the user the ability to understand how the model works, in the sense that you can compare your patient with some other patients that are similar with respect to the features. Then we have KNNs. They're also nice for exactly the same reason. You can get the neighbors, you can return the neighbors, and then people can understand, at least locally, what's going on with the model. What are some other patients that look like my patient? What happened to them? They're the same age. They're maybe smokers if my patient's a smoker, and so forth. So these are, in an organization, if you're trying to get started with machine learning, you don't have a very complex problem. What I mean by that is there's not a lot of interactions, not a crazy amount of features. You have the typical tabular problem. I don't know, you have 10 features and you have a couple of thousand observations, maybe more observations, maybe more features. But it's not like a crazy problem with a lot of subtleties and things like non-linearities and things like that. It's a straightforward problem. These models will often do just fine. So at least try them out in the beginning of your project. Now we're going to switch gears completely. So far we just talked about simple models, and I urged you to try out simple models. Now we're going to talk about math, and we're going to start with linear regression, and we're going to build our way up to generalized additive models and explain what they are and show some examples of modeling towards the end of the presentation. So switching gears completely, let's start with linear regression. We have a data set X, that's a matrix. We have a vector of observations Y. And we have this loss function, which is the sum of the squares, or sum of the squared residuals, I should say. So X beta is the prediction, Y is the target, that's known. We're trying to find the beta that minimizes this loss function, L. And here's a question for the audience. There is no audience here, so I'll answer it. But the question is, why do we like squared errors? Why aren't they raised to the power of 4, for instance, or some other crazy function? What's so good about squared errors? Think about that for 10 seconds. So, well, there are many reasons. The square is symmetric, so if the residual is positive or negative, it always returns a positive number. It's differentiable, so you can compute the derivative and you can use that to tell you in which direction to go. Also, the squared errors, from a statistics perspective, the squared errors is it's equivalent to assuming a normal distribution. And if you don't know a lot about the distribution, assuming a normal distribution is often very sensible, because the normal is, under some conditions, it's the distribution that minimizes the entropy, I believe. And there's also an optimization reason why the squared errors are nice, and that's because of if you look at a Taylor expansion of a function, if it's a square, then the Taylor expansion, you capture everything if you go up to the second derivative. So if you're minimizing the squared errors and you compute the Hessian, you have the second order Taylor expansion, you have all the information you need and you can kind of one-shot the optimization problem. So you can solve squared errors in just 1 Newton step, is what I'm saying. But if you used squares to the 4th power, that wouldn't be the case. So all the information of a squared error is contained in very few terms in the Taylor expansion, which is a nice feature when we're trying to optimize this thing. So how do we solve it? There are many ways. The most straightforward way is to use the definition of the squared norm, write it out like we do in the top equation here, multiply it through, differentiate it, set it equal to 0, and then solve for beta. You get this equation, or these equations, called the normal equations. And you can form these, you can form x transpose x and x transpose y on the right hand side, and you can give this to a solver and you get an answer back. That's the most straightforward way. There are of course other ways to do this. You can look at the references at the end of the presentation for more details, but you can compute the singular value decomposition, the QR decomposition. There's iterative methods, and advantages of these are that you don't have to form the x transpose x, because that will make the numerics less stable. So there are more stable ways to solve this. In practice, to be honest, it doesn't matter that much for most data sets. You'll probably be fine. If you have huge number of features or variables, these matrices become large, maybe even sparse, and then iterative methods could be a great option. There are many ways to do this. One way to learn about it is to just go look at software like scikit-learn and see how they do it. They have implemented many ways of solving the you can look at the ridge implementation, for instance. Now, if you're not following the matrix calculus here, that's fine. I would then urge you to minimize a scalar function. So look at the question at the bottom of the slides. Choose a number x and y, and then use your calculus knowledge to solve for the optimal beta. So set x equal to 2, y equal to 3 or something, and then use calculus to solve for the optimal beta. That's a good exercise and a good way to get started. And the 1D example closely mimics what happens in arbitrary dimensions, actually. It's just working with matrices instead of numbers, which is a bit more involved. Now we're going to go from linear regression to ridge regression. We're also going to add some weights to the data, because it's a common thing to do. You have the option of adding weights if you deem some data more important than others. Some examples. So we're going to do two things to the loss function. The first thing is we're going to add this W matrix. That's we're going to use a weighted norm, I should say. The W is a diagonal matrix with weights, and they are always, I believe, greater than 0. I've never seen people use negative weights. There might be some reasons to do that, but we can assume that these are positive for our purposes. The second thing we do is we add this penalty term, alpha times the squared norm of beta, and that will, for alpha greater than 0, this will pull the beta coefficients down towards 0, effectively regularizing the solution towards 0. So a good question then is, why does adding this regularization term help? That's the question here. I'll give you a few seconds to think about it. Well, it will pull the coefficients towards 0. So what it's saying is that we believe all coefficients are 0 unless we see proof otherwise. So like if you have two data points where it looks like a non-zero coefficient will help, the non-rich version would just fit to those two data points. But with the rich regression, it will say, well, two data points, that's not really that much evidence, so I'm going to regularize it towards 0 unless I see more and more evidence in favor of something else. And especially if you have many features and so like imagine you have 100 features and you kind of don't know if most of them are good or not. But you suspect some of them are good, like 10 of them. Then Ridge will hopefully pull most of these very close to 0, like 90 out of 100 or so will be pulled towards 0. And the remaining 10 will probably be picked out as good features, having larger coefficients. In practice, you choose the value for alpha by cross-validation. And I think that's all I have to say about Ridge for now. So how do we solve this thing? Sorry, before we talk about solving it, let's look at what the modeling would look like. So here's a data set from powerlifting, which is a strength sport where it's a very simple sport. People just show up and lift weights, and the person who lifts the most wins. So here I have body weight on the horizontal axis and total weight lifted on the vertical axis. And I fit a ridge with 3 different penalties. So with no penalty at all, we get the blue line, which fits it's just the ordinary regression line going through the data points. And you can see with some penalty and a really strong penalty. With a strong penalty, the coefficient goes to 0. There's still an intercept that's not penalized. But what happens is it's just pulled towards 0, so it's just a flat line. And in more dimensions, it would be a flat hyperplane. So in Ridge, the relationship must be linear and additive. By linear, I mean it's linear in the engineered features. We can still engineer some features. By additive, I mean that we have to add the effects of individual features up to get the result. So if we're looking at modeling the price of a car, and we know the car's age, and we know how long it's driven, like how many kilometers it's been driven, then the effect in a additive model is the effect of age and the effect of kilometers driven added. That might not be a good model for the real world always, so that's something to be aware of. Is the additive assumption good or not? But the linear assumption we can kind of deal with. If we know the truth is not linear, we can engineer some features. So for instance here, total weight lifted, body weight. I know that there's a diminishing return when body weight increases. You're not going to get stronger at the same rate. It's going to be diminishing as your body weight increases more and more. And I could engineer a feature for that. Maybe I would assume it's a logarithmic relationship or some other relationship. I know a little bit about this, but I'm not going to get into details. But the point is there's a diminishing return and you can model it somehow. Yeah, we'll leave it there. So here are some examples of feature engineering, like time of day. If you have some periodic phenomena, you can map your time of day t to a circle. So that would be t here, I guess, would be in the range between 0 and 24. So it would be like hour of the day. And you can map that to a circle, and then a linear model can work on that circle and pick out certain phenomena that occur at certain times of the day. House prices. So imagine you have latitude and longitude. You're trying to predict the the price of a property. Do you really believe that there's a plane sitting above the latitude and longitude that tells you the price of the housing, of the apartment or the house? Probably not. In some cities there might be something like a plane, like going west to east. That's thinkable. But you probably want to engineer some features like distance from city center. Typically, it's more expensive to live near the city center, whereas if you live in the outskirts of the city, it's more cheap. So you can use some domain knowledge, engineer some features, and that can probably help you quite a bit if you want to work with a linear model. So the question here, can you think of nonlinear and or non-additive problems? I already kind of answered that with these examples above, so we're just going to skip ahead. So to solve the ridge problem, we do exactly what we did for the linear problem. We multiply out the loss function using the definition of the weighted norm. We get this first line, then we compute the gradient with respect to the vector beta, and we get this gradient term. That's the equation in the middle here, and we set that equal to 0 and collect terms. And then we obtain, yet again, normal equations. They look a lot like the previous normal equations, but we have this weight matrix, diagonal weight matrix W in between x transpose x, and we have this alpha times the identity matrix here too. On the right-hand side, we also have the weight matrix. But apart from that, it looks a lot like what we saw previously when we just talked about normal linear regression. And again, if the matrix calculus is unfamiliar to you, but you know calculus in one variable, please look at this loss function in one dimension. Try to pick some numbers and minimize it, and see that what you get is something very similar to the matrix calculus equations. Here's a neat little trick that we could use. It's always nice if you can reduce one problem to a problem that you know how to solve, and this is a theme that we'll get back to later on in the presentation. So recall that the squared norm of A plus the squared norm of B, that's just A transpose A plus B transpose B. And that's just this vector AB if you concatenate the entries. AB row vector times column vector. And again, that's just this concatenation of AB and the squared norm of that. So if we know that, and we assume that our weight matrix is positive, and our alpha is positive, or 0 in the edge case, then you can actually take the objective and make it into a ridge problem, which we know how to solve, with some new matrices x prime and y prime. And this is a way to solve the problem. So you can take the ridge problem, reduce it to you take the ridge problem and reduce it to a general, just a linear squares problem that we already know how to solve, because that's what the ordinary linear regression solves. And you can use whatever algorithm you use to solve that problem to solve this problem. In practice, you might not do this. It's a bit slower, I believe, but it has some nice properties when it comes to numerical stability, I also believe. So not saying this is what's done in practice, but it's a nice little trick, nice thing to know about. And it's cool to be able to reduce a new problem to a problem that we've seen before. If we have a solver for that problem, or we have a solution approach. Okay, so we've seen linear regression, we've seen ridge regression. Now we're going to do ridge with one added complexity, and that's a link function. Technically, it's an inverse link function. So consider a case where y must be positive. Could be the price of a product, price of housing, could be a cholesterol level, heart rate, salary, whatever, but it's positive. So what can we do? Well, one thing we could do is we could just use a normal linear regression, and then if the output is negative, like we get a negative cholesterol value, you could just map it to 0 and just hope everything's okay. That's a bit uncomfortable though. Like if you're predicting negative values, it's a bit strange. Maybe you want to raise a warning in a real software system if you get some crazy outputs. That's one way of doing it. Is just kind of ignore it when you're choosing a model. The second thing you could do is you could take the logarithm and fit it in log space. You can fit log cholesterol. But then the issue is you're not doing least squares in your original space, you're doing least squares in the log space, and that's not the same thing. So if your least squares assumption is true in the original space and you're fitting on log space, you're doing something else entirely. So it's probably not what you want to do. Sometimes it is, but then you wouldn't have the least squares assumption in the original space in the first place. Well, here's a thing we can do, another option. We could introduce a function h that maps to positive numbers, and we can minimize h of x beta minus y instead of x beta minus y. This way, our predictions will always end up positive. One option for such a function h would be the soft plus function. And that's a smooth approximation to the function max of 0 and x. So max of 0 and x, it's just 0 all the way to the origin, and then it goes up like y equals x. So it's like a hinge type of function. The soft plus is very similar, but it's differentiable and more smooth. Also, just as a comment here, if you implement soft plus, don't implement it like this, because the exponential will overflow very quickly. So like if eta here is 100, x of 100 will overflow. You'll do log of inf, which will be inf, and then the whole thing overflows. So, but thankfully it's simple to get around this by just thinking about numerics a little bit, but don't actually implement the function as it's written here. This is just a mathematical definition. It's not how you would implement the soft plus function. Okay, what about the optimization problem? Very similar to ridge, but with this inverse link function h that maps from an unbounded linear space to this target space, we could say. Like the target space could be positive numbers, could be fractions between 0 and 1. This will complicate the optimization routine a little bit. We're going to have to do it in a different way. But first, a little bit more about modeling with an inverse link function. Another example is shown here. We have some kind of target that's a percentage, or it's in between 0 and 1. And here it's the score on a test versus study hours is the feature. And the score can be between 0 and 1. So it's a bit uncomfortable if you predict 1.1 from your model. And here I just show the difference between fitting a ridge and fitting a ridge with a logistic inverse link function. So yeah, if you need positive values, sales prices might be a good option. If you want fractions or numbers between 0 and 1, or something like you have limits on both sides, the price would be a limit on a lower limit. But if you have a lower and upper limit, then maybe a logistic function would be good. If you believe in multiplicative effects, then you could use an exponential function here. And what that would do is it would make the features multiply together to produce the result, which might be reasonable in some problems. Or whatever else you like. Okay, so how do we optimize this thing? There's always the first order methods like gradient descent, just using the derivative or the gradient of the function to make a step in the correct direction. You could also use second order information, which means computing a Hessian. And I see two ways of attacking this problem if we want to use second order information. We could do a Taylor expansion of the inverse link function h, or we could do a Taylor expansion of the whole loss function L. And one of these is called the Gauss-Newton algorithm. The other one is called Newton's method for optimization. And again, the homework here, if you're interested in this stuff, is to try to implement these methods. I'll explain how they work. You could try implementing these in Python. It's maybe a bit tedious to do it by hand because it will be an iterative algorithm that will converge to a solution. But you can implement it in Python or maybe even in Excel or something like that if you work out the equations. But the point is, it's interesting to try to solve these problems in one dimension before you generalize to the matrix case. Here is a one-dimensional example. There's the loss function. I use the soft plus beta. X is just 1, so it disappears here. I want soft plus of beta to be as close as possible to 4. And the true value looks like beta should be around 4, which makes sense because the soft plus for positive values, it's more or less the identity function. But for negative values, as we see here, it's not, it goes to 0. So on the black line, it kind of evens out on the left here, and it will just flatten out. So we have this loss function in black. We're at this point 0. That's our starting point. If we do an expansion of the inverse link function h and we minimize it, we would move here to approximately 7, a bit below 7. Then we would expand again and hopefully move to the left, and it will converge towards 4. If we do an expansion of the loss function, the Hessian is actually negative, which means you get a parabola that goes down. And that's bad because then you don't know, well, it will tell you to go to the right, but it will tell you to go infinitely far to the right. So then what we would do is we would force it to be positive definite. We'd make a step to approximately 3, and then we would keep iterating. So we're going to look at both the math behind both of these techniques, Gauss-Newton and Newton's method. Here it's important to not get bogged down on details. It's just, I want to spell out the math if you're interested, but it's not like the details of the equations is not what's important. The takeaway here is these methods for optimizing these functions that become more and more complex, where you can't just differentiate it and set it equal to 0 and solve it in one go. You need iterative methods. And in the references at the end of the presentation, I'll refer you to some books on optimization where you can learn more about this stuff if it's interesting to you. So here's the simplest one. You take your simplest approach. You take your function h and you expand it around some point beta L, which is the current estimate. Maybe you just start at beta L equals 0. You get this linear approximation, Taylor here, first order Taylor, and then you plug that back into the objective. So you take this h function here and replace it with this thing, and then you collect terms, and what you will see is that you end up with a ridge problem. So you get x prime, a new matrix here, that's a diagonal matrix times x, and you get this y prime, this vector, that's this part. And then this is just a ridge problem. So we know how to solve ridge, we've seen that before. So if you know how to solve ridge, you can actually just iteratively solve ridge problems. You start out with some beta L, you solve this ridge problem, get a new beta L, and you plug that in and you solve it again. Typically, a few iterations of this will converge and give you good results. Here's the second approach. using Newton's method, we'll expand the whole loss function, and Newton's method is this. It's the next beta is the previous beta minus the inverse Hessian times the gradient. So what we need to do to make this work is to get an expression for the gradient and an expression for the Hessian. I find it, the way I find it easiest to do this is to write out the loss function and actually switch notation a little bit. So I go from matrix notation to summation notation over the features, over the observations, not features, I. So over the rows of this matrix X. And then I differentiate in summation notation and then bring it back to vector notation. If you're better than I am at matrix calculus, then maybe you can do it just in matrix calculus, but it's not something I do every day, so I tend to forget the details, and then it's good to be able to lean on the more familiar summation notation or do one D examples and then generalize after the fact. But I'm sure if you sit down with this, you'll be able to figure it out. In the worst case, what you do is you write out some 2x2 matrices and see that things work. It's mostly just a bit of labor. It's not very hard. It's just a bit unfamiliar, perhaps. Okay, so let's look at the gradient and the Hessian without worrying too much about details. So we just take our loss function, differentiate with respect to beta, and we end up with this. It's quite simple. It's just the 2 goes down, and then the inner part here gets differentiated. You get the gradient with respect to h, but h has this really nice linear structure here in the arguments. So you just differentiate that pointwise and then bring out the xi here. It becomes a transpose, so this is now a column vector. Then I bring it back to matrix notation, where it looks like this. This is just a number 2 matrix, diagonal matrix. So if you implement this, you don't want to multiply. You don't want to explicitly create the diagonal to multiply. So remember that if you're multiplying a diagonal matrix on the right, you're really just multiplying each column of this matrix here by W. So you don't actually form the diagonal matrix and multiply it. You just multiply each column of X transpose by the diagonal elements of W. Once you've done that, you have this matrix term here. This is you have a vector term here. This is a vector, this is a vector, and this this dot with the circle, that's just the element-wise product of the entries of A and B, these 2 vectors. So just to remind ourselves of shapes, the gradient here is a vector that has the same shape as beta. So we differentiate this thing once more and you obtain the Hessian. It gets a little bit more involved, but it's not too crazy. Shouldn't be surprising here that you have h differentiated twice, right? And then you have it differentiated once to the power of 2 here. You can work this out if you want to. Not going to do it in detail here. After working it out, I pull it back to the matrix notation and it looks like this. So now that we have the gradient and we have the Hessian here is of course of shape. It's a matrix of shape, length of beta rows, length of beta columns, and it contains all the second derivatives along the rows and columns. So after working this out, I wasn't sure if I did it correctly. Will it work, right? So I just decided the simplest thing to do is just to implement it and see if it works. If it doesn't work in my implementation, then I probably made some error in the math, which is not completely unlikely. But I was happy to see that it works. The math seems to check out. Here I did an experiment, created a data set with 1,000 observations, tried it on 10, 100, and 1,000 features. The inverse link function is just soft plus. What I here call Newton is Newton's method, using the Hessian and gradient. ILS is iterative least squares. That's where I expand H. Auto is just my own little method where I do every other routine. So I do 1 Newton step, 1 ILS step, 1 Newton step, 1 ILS step, and just iterate back and forth between the two methods. And the idea there was that maybe if one of them is slow, the other one can help speed it up. And then I verified all of this against SciPy, and on the y-axis I plot the number of correct digits after the decimal place. So you can see here that it beats SciPy typically in 3 or 4 iterations. Typically gets 12 digits correct after the decimal point. Looks very good. The number of iterations, we run into some problems when we have 1,000 features for the ILS method. It seems like it's not taking, it's taking steps that are either it oscillates back and forth, I would guess, or it takes steps that are just not long enough. Either way, it's slow to converge. So then the auto method, where I just do a step of Newton instead, seems to really help. This might not perform well on non-convex objectives. We saw that already, that we have to make sure the Hessian is positive definite, so we get a sensible step length. But even then, it's not always you can't always trust that the step length given by the Hessian is good. So what we typically do is we do some kind of line search. We use the Hessian to tell us what direction to go in, but we don't necessarily take a full step. We might do like halving search, for instance, where you tried a full step, and then if that doesn't improve the objective, you do half a step, and then a fourth, and then an eighth, and then a 16th, and so forth, and then stop when you get an improvement in your objective. So should you use Gauss-Newton or Newton? Well, it depends on the problem. There's no, to my knowledge, there's no method that always beats the other method. All right, so finally, we get to generalized additive models. So now we're going to forget a little bit about the math, but it's going to be very similar to what we've seen. We have to explain what a generalized additive model is first. This is going to take 3 slides or so. So if you don't understand everything in the first slide, bear with me. This explanation might not be the best, but I really hope I can show you the basic idea. So instead of just having a numerical feature and fitting a straight line to it, just imagine one feature, one target. Just a regression on one variable. It's the simplest thing. We're going to expand numerical features using a spline basis, which looks like this. These are 3rd order splines. I believe they are continuous to the 2nd derivative, so very like nice smooth functions and local functions. So they don't go out to infinity. They really do go to 0 and stay at 0 once you get out of their domain, or their what would you call this? Well, my point is that they do go to 0, right? So they're local functions is what I'm trying to say. When it comes to the loss function, we are going to do 2 things. One of them is that we're going to create more columns in X to accommodate the spline basis. So here we have 6 spline functions. So one feature in X would become, one column in X would become 6 columns, where we have taken that one feature and expanded it and evaluated it on these 6 spline basis functions. That's one change that we're doing. The second change is that we're not going to penalize just the size of beta. We're going to introduce the 2nd order finite difference matrix D, and that's what we're going to use to penalize. And that's going to approximate the 2nd derivative. And the second derivative of a function is how smooth the function is. So a linear function is perfectly smooth because the second derivative is 0. But if you have a wiggly function, like the sine function or just anything that's wiggly, it has a non-zero second derivative, and it will be penalized in a generalized additive model like this based on spline functions. Now, the generalized part means that we can use other probability density functions to model our target. So far, we have implicitly assumed that everything is Gaussian when we used squared errors, but you can, for instance, do a poisson regression, or you can do a logistic regression, or you can even do like a gamma regression in the framework of generalized additive models, and that's what the generalized part means. Okay, let's look at this in a bit more detail. Here is what the second order difference matrix looks like. It's based on this approximation to the second derivative, and it will multiply the coefficient vector beta and penalize wiggliness. Here you see data in black in the bottom figure. You see the spline basis around 0, the basis functions, but they have now been multiplied by respective betas to produce the blue curve. I have removed the intercept. So what I'm saying is, if you take your spline basis and you multiply them by these optimal betas, which have been found, and you add them together, you get this blue line. That seems to fit the data really well. Data is generated by a sine curve here, but with 6 spline basis functions, we can model this. And we don't get a lot of wiggliness because I penalize some wiggliness here, but you're not going to get crazy wiggliness with just 6 spline basis functions anyway. So here's some more practical examples showing how to make models. We're going back to the powerlifting data set because I think powerlifting is interesting and a cool sport. So I want to model the strength of powerlifters as a function of their age and their body weight. So I model strength as a normal distribution, and I model the mean as a spline of age plus a spline of body weight plus some constant c. And I use a log link. So my inverse link function would be the exponential. What that means is that I'm assuming a multiplicative effect instead of an additive effect. And I think that makes sense for this problem. I think that age, no matter what body weight you are, there's an effect of age that acts as a multiplier on your body weight, not as something you add to your strength. And what that means for the y-axis is that the factors you see are multiplicative. So you start with 0.8, which means like 80% of the strength, and this is all relative, so you have to compare it to something. So here at around 30, it seems like lifters are the strongest, and then the effect is around 1.2. So then you could reasonably say that you go from 0.8 to 1.2. So that's like a 50% increase in strength from when you're 15 to when you're 30 if you're a powerlifter who competes in powerlifting and lifts actively, right? And then we can also see that as you get older, your strength will likely go down. This is very interpretable model in my view. You can see the data in the background. You can see the trend. We didn't have to do any feature engineering here. This is we don't see the spline basis functions, but this is a sum of spline basis functions. And you really learn a lot from your data. You see this sharp increase and the more slow decrease. You see that the strongest lifters are around 30. And for body weight here on the right, you see the diminishing return as people get heavier. We don't obtain an equation for this line. But we can plot it and we can see it. And since age and body weight are independent in the sense that there's no interaction between them, we can just plot them individually, right? So Some caveats. The effects are still additive. So I'm assuming here that the effect of age, for instance, is independent of the effect of body weight. Like, I'm assuming that the model assumes that the strongest lifters are around 30, whether they weigh 60 kilos or 100 kilos. If there was a more complicated pattern to this, like if lifters were 120 kilos, then actually the strongest age is around 50 years old or something like that, then this model is not appropriate. I would have to think of a different model. So I'm imposing something in my modeling here. It's not like a boosting model where I can just give it data and it will just work in a space where anything is possible. I'm constraining it with my prior knowledge, but it seems to me perfectly reasonable to say that age and body weight, there are no interactions between the two. If lifters truly are strongest around 30, that's probably true whether they are 60, 80, or 100 kilograms in body weight. The nice thing about the additive model is that linearity is no longer a requirement. So I don't have to do the feature engineering of each feature. I don't have to assume that it's linear. That the spline basis will help me and will pick out, and I'll get these functions. I can get the uncertainty, as you see. So unfortunately, perhaps this is the only model that I show in this presentation. Maybe I should have included a few more just to kind of convince you how useful this is. But you can imagine in other data sets that are kind of like this, where you want to understand relationships between the variables. These models, generalized additive models, are a really useful tool, something worth considering. I hope you're convinced of that. Well, what if you have interactions? You can get around it by adding these tensor splines. So here's a data set that kind of mimics the XOR function. So here we have x1 and x2, and if x2 is a low value around 0, then increasing x1 increases the target. You go from dark colors to bright colors here. But if you increase x2, the opposite effect occurs. You start with high values and then go down as you increase x1. So you can't model this with a plane. Like, there's no plane you can fit in that would be above this data set and capture it. And not only can you not model it with a plane, as you would have to in ridge, you can't model this with an additive function either. So you can imagine choosing some additive function over one feature x1, and then over x2, and then adding them together, trying to produce this, and you can't. So this is a non-additive data set because we have an interaction term between x1 and x2. And then the question is, how does this work in a generalized additive model? You can get around it. What you do is you use a tensor spline term. A tensor spline, instead of having a spline basis along each dimension individually, so if you have 10, you would have 10 along x1 and 10 along x2. You actually take this tensor product of spline bases, and you get the 10 by 10 grid of functions. Imagine them being like little mountains here. And then you're trying to figure out the height of each of these 10 by 10, 100 little mountains to match this data set. And here, when I fit it, you can see the outline of the tensor spline here in the second figure. In the third one, you can see a surface plot, and you can see that it fits this data set perfectly, more or less. The cost is that you go from having 20 coefficients, 10 for each feature in this case, and adding them together, to having 100, because you take 10 times 10 and you make 100 little mountains, little functions, local functions that we're trying to add together to produce this surface plot. So you don't want to overdo this, but it can be really useful. Like, say you're modeling, again, house prices. You could add a spline for the square meters of the house, and then you could add a tensor spline over latitude and longitude, and that could pick up the geographical effects. That would be a quite sensible model for something like house prices. But you wouldn't want to add square meters in a tensor with latitude and longitude, because, or we assume that, for instance, this higher the number of square meters, the more it costs. And that's the case over the entire range of the geography, wherever you are on the map. So we don't assume there to be any, at least not any strong interaction terms between the latitude and longitude and the number of square meters. So again, we have to do some actual modeling and think a little bit. We can't just feed it into the model like we can with a neural network sometimes, or a boosting model. You can get really far just giving it the data. Here we have to think a little bit more, talk to some domain experts, and do some modeling. As a final comment, everything that we've talked about so far is based on squared residuals, and this is equivalent to minimizing the negative log likelihood of the Gaussian. So if we start with the Gaussian or normal distribution, you might remember this this formula for it. The likelihood is just the product of all the data points, so that would look like this. And then if you take the negative log likelihood, you have to take the logarithms, the squares go down. The second thing here is just this logarithm becomes constant. So the mean is independent of the standard deviation. Nice property. You can pull out this standard deviation here, and then more or less what you're left with is just the squared residuals. So there is some misunderstanding about this sometimes. People sometimes think that if you're doing least squares, you have to believe the data, that the data is normally distributed. That's not true. You're minimizing, you're optimizing for the mean, and it is true that minimizing, how should I put this? You don't have to enforce a probabilistic argument in order to use least squares. You can just minimize, you can use least squares, just minimize the squared residuals. That's perfectly fine. You don't have to use a different distribution, even if you know your data is not normal. However, it is equivalent to minimizing the Gaussian, and if you take that perspective, then it might make sense. Depends very much on the purpose of the model and what you want the model to accomplish. But then it might make sense to check if the residuals are actually, like using a QQ plot, if it's normally distributed. But there's nothing wrong, at least in my book, there's nothing wrong with using least squares, even if you know your model is not Gaussian. It's a bit like using the mean when you have some outliers or something like that. Maybe you know you have some outliers, but you still use the mean. You don't go for the median. It's just a modeling choice. You have to be aware of it. But they are, in a sense, two sides of the same thing. Whether you start with a Gaussian, you minimize the negative log likelihood, or you just assume sum of squares, you get the same equations. Hopefully that was somewhat understandable. But we can use our framework with the splines for other distributions, Poisson, Bernoulli, which is logistic regression, binomial, gamma, inverse Gaussian, and maybe a few others too. And to do that, we just replace the sum of squares in the objective with the negative log likelihood. So for instance, for the Bernoulli distribution, we have this likelihood, P, and then the negative log likelihood becomes this expression here. And then we have to choose a link function or an inverse link function, and then it would typically be the sigmoid. It turns out that this is something called a canonical link function in this case for logistic regression. But you have to map so that your predictions become a number between 0 and 1, and using the sigmoid, I hope you agree, is quite natural a natural function for that purpose. So I don't want to dwell too much on this. You can check out the references if you're interested. I think the most important thing to realize or to understand is the Gaussian case and how it relates to these to ridge and ridge with an inverse link function, and then you can take a less of an optimization approach, which is what I have tried to do, and more of a statistical approach if you start with distributions and you look at log likelihoods instead. So in summary, performance of a model is, using a model is about way more than just the performance metrics. And in Kaggle competitions and machine learning competitions and papers, people obsess over performance. But in the real world, if you're working in industry like I am, that's just one of your concerns. You want to make a model that people feel comfortable using. You want to get it out the door in a reasonable time. You don't want to spend a week training this thing if it can be done more quickly. And many companies aren't Google or Facebook. They are not as big. They don't have the resources. And if they're also not companies that already use machine learning, it makes sense to start with something simple. So that's like the practical argument for using simple models. But it turns out that simple interpretable models are often competitive with respect to performance too. Like if you take the powerlifting data set here and you go for a boosting model, you're just going to do marginally better, like a percentage point or two maybe. And you lose so much interpretability. So I think if your data set or the problem you're trying to model is not that complex, that's also an argument for choosing a more simple model. And then you'll be able to understand how the model works and what it's learned in a way that's a bit more tough with boosting models. Though there are some excellent techniques for trying to understand black box models. But in the end, you're putting things on top of the model, trying to peek at it and understand what it's doing. The actual model has all these interactions. It's highly nonlinear, and it's tough to really understand what it's doing. So in my view, the generalized additive model strikes a perfect balance in many cases between interpretability and predictive power. And it's something to consider at the very least, though it's not the solution to all your problems for sure. There's a reason we have different models, and there are many considerations to make for each project, so it's hard to make general guidelines. Another interesting final point here is that you can often extend models if you know the math behind the models. So this is an argument for understanding the simple stuff. By simple stuff, I mean like tree models, linear regression, regularization techniques, all these things that are well known. If you understand them really well, you can typically modify them a little bit and solve problems with more specialized algorithms. I'm not sure if I would recommend doing this in industry, in practice. Sometimes it's really nice to just rely on a good implementation in some software, and you don't want to mess around too much making something custom if you don't need to do it. But on the other hand, sometimes you don't want to reinvent the wheel. You just want to take something that's well known and make some slight modifications to it, either to the math or to the code, maybe by subclassing some estimator and scikit-learn, and that will perfectly solve your problem. So be a bit careful here. Don't go crazy making your own stuff from scratch or anything like that. But if you know the math, you can extend some of these well-known models and solve your specific problem. So this is not just machine learning, just in applied math and using math to solve problems in industry, most problems are just a slight variation of already known problems. And that's a very useful thing to know, because it means you can lean on all the fantastic work that's been done in the last 50 or 100 years. You can probably find papers if you know what to search for, make some slight modifications, and you can solve almost every problem that's out there. not the new novel stuff that people are thinking about, of course, but like most of the practical problems that the common typical business organization faces is just a variation of a known problem. Now I'm rambling. Here are some references. I'm working on a little Python package for generalized additive models. It's not production ready yet, but maybe if I keep working on it, it will be. Feel free to have a look at the code. Maybe it's interesting. If you want to contribute, I'm very open to pull requests. Just make an issue first, so I know what you're working on. I really recommend The Elements of Statistical Learning, even though it's a tough book. It requires a lot of knowledge about math and statistics. It's a really good book to have lying around. There's a book on Generalized Additive Models by Simon Wood, also very good. I recommend it, not to everyone, but if you're interested in these types of models, then I highly recommend it. For optimizations, there's Convex Optimization by Stephen Boyd, and Numerical Optimization by, is it Wright? I'm not entirely sure. I'll put the slides for this in the YouTube description, so you can go click on these links. There are also two papers that I really recommend you read. One is an argument against black box models, and the other one is an argument for black box models. I'm not sure if the authors of these two papers would necessarily disagree with each other, but they have some different opinions, and I think it's really interesting to read both of these. Personally, I might be more after working with this for a few years now. I'm leaning more and more towards really the simple stuff, at least starting with the simple stuff. But read both and make up your own mind about this. All right, thank you so much for listening to this presentation. I hope you learned something, even though it was an unholy mix of of a lot of topics, with the detailed math and some aspects, and a little bit about the explainable models, and a little bit about this and that, and some modeling with generalized additive models. I hope you got something out of it. So thanks a lot for listening to me. Bye bye.